Hello. Yeah, better. Hi, everyone. So this morning, I want to talk about the real-world scenarios where we can implement deep learning models, and then we can scale it to the market. So a lot of time, we start working with these models in lab. We experiment. We try different things. It works very well, but the moment we try to take it to the market and in the production, it fails terribly. And that's where we have to be very attentive, like how we can deal with it, and what precautions we need to take when we take it to the market. So I will go with 2 or 3 use cases where I'll show you how a very simple use case where we can use the deep learning models for the production purpose. So just to give you, how many of you are quite aware of telecom here? Financial industry? Okay. Anyone from telecom? Okay. So the use case that I want to discuss here, it's very common, like mostly around the time series prediction. So if you deal with a lot of money in the markets, you must be aware of it, and you must have tried to predict some of the sales value. So it's very common, and you try all different techniques to get it right. So the very similar technique, we applied it for a network congestion model. So the data was to find where we can forecast the next congestion. So in a telecom sector, we have massive amount of data coming from more like IoT devices coming from everywhere. You can expect 30 gigs of data getting generated almost every hour if you are capturing a lot of information from everywhere. So now that's a lot of it. And now how you deal with it, how do you predict a model, run a model that can predict or forecast, and then in real time you can get the responses so that you can work on it. So also it becomes important that how do you predict and forecast between them so that you prepare yourself better for those anomalies or those faults in the future. So I'm going to talk, so first, say if we have the congestion data, if we have the network congestion data, then how can we predict and what will happen in next 24 hours, and what are those different the faults that may come up? So again, it's very important that we understand the different sources of data for this, and then how do we apply different techniques? Because you can go from a very basic model, a traditional approach, to a very advanced deep learning, reinforcement models, some of the sequence modeling with a recurrent neural network. But the challenge is how you get the best output for the production purpose. Okay, so in most of the cases, these cases, wherever the events are related, you can put those data on definitely on the time series. That means if you have the logs, if you have the dumps from IoT devices, from the events somewhere, say if it's the sales data on, or you're getting the Bloomberg chats, you're getting some of the preventive prediction models, like where you have a lot of data coming from the sensors, then you start picking up all those data and try to make sense out of it. And the easiest way when you have so much of data to deal with it is to transform it into time series. And if you want to understand the pattern, what's happening. So the way it works, maybe if I can use, okay, so when you put your data, because most of the time your data will have those timestamps, and it's easy to transform the timestamps on your timeline. But now how are you going to use it for your forecasting? Okay, great. So at any point, say this is 30 days of data. Now what happens you have massive amount of data flowing through all the different sensors. So say sensor 1, or the devices 1, devices 2, 50, it goes to like 100,000 devices at any point of time. So when you are dealing with the data, you're not just dealing with one, say if you're putting the pattern of that data, it's not just one device that you are dealing with, you are dealing with the hundreds and thousands of time series simultaneously. So now, how do you deal with it? So the easiest way to work with this is, say, if you want to predict it for the next 24 hours or for next 1 week, so you block here on 21. Now, what do? So for the first 7 days, or say, you will create that, more of a supervised model. So you will create the first 7 days of data, and then based on that, you will take the 8th data as your label. Now, that's the easiest way to do. There are a lot of ways that you can do it, but how do you come up with a very good accuracy, very good recalls on that? That's the question. So then you move the data sets, the timeline. So then for the next day, your data will start from 2nd till 8th, and 9th will be your label. So based on the pattern that you see from 2nd to 8th, you predict that what happens on 9th. If you have any question at any point, please stop me there, okay? So, and that's how you go. So you start creating all the data sets until, say, 21st from 14th to, and then you predict it on 22nd. So this is how you start predicting the time series. This is how you create the label data, and you start the prediction. Now, this is very handy for any kind of anomaly detection, any kind of preventive maintenance, markets data. The next challenge would come is because you're dealing with lots of other devices. So if you're dealing with thousands of devices and the thousands of time series, how you work with it. Let me give you the real world example from the data so you can understand what I'm talking about. Sorry? Yes, I will come to that. I'm just talking about the preparation of the data, but I'll come to the different techniques that you will apply to it and how you will get results out of it. Okay, so this is just one data set. So this cell ID says these are the different devices, and they're all different configurations. So in our example, where we have taken network data, network congestion, it talks about all different call drop rates, call success rates, all different KPIs that we need to understand for any network model. Now, based on, and we also have the labels here, like whether it was a congestion or not. So you can see it has a voice congestion or the data congestion. So based on, and you can see these components will change. So now, because you have a lot of components, what are the other challenges? How, if you're creating that data set with time series, what will happen? A clear, like a problem that comes here. So when you're moving between the data set, like how do, depending on how you're transforming your data, say if you create your window here from 1st to 3rd, and based on that, you are creating your prediction here. Now, as you move your data here, in real world scenario, you will have this kind of data where, so you will be moving your window like this. So you're moving window up and down. So what happens at certain point, like, because you have taken the window of 7 days, and if it's not there, to give you example, say it's device 1 here, and it's device 2. and you have device 2 data here. When it ends, usually, as you move, it will capture the data from device 3. So what I mean, when you're creating the time series, the usual fault that you are where you can really miss out on this technique is when you have these multiple devices, you can easily move, like you can mix the time series or the this time series of one device into the other device. And that's a very regular mistake that anyone does. So you have to be very careful when you are dealing with those things. Yes. Yes. Okay, so usually what happens, depending on how you have created your data, so say if you have created your timelines on column, so this is date 1, 2, 3, 4, in your data set, you will move your you will move your time window like this, in this direction, 2, 3, 4, like this. Yes. 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 So, so if the you're asking if the data is on X. Okay. The way I have done it here, because I tried both the methods from what. So I tried both the methods where I tried to pivot the table so that I can put the dates in the columns and deal with it, but the difficulties or the complexities were even much more than that. So then when you're moving your time window, so I stick to this approach where it was much better to deal with it. And that's where the only challenge that I had to deal with it is not to mix the time series from the different devices together. So that you can easily deal with it. Okay, so like for the network modeling and for any other use case, it's not always just one device that will give you the prediction or the output. You will have a lot of dependencies on other devices. So device 1 or the sensor 1 will have the dependency on sensor 2. That means if it shuts down, then there will be this device 2 will be overloaded. In the network scenario where you have, say, a base station where you have 5 to 6 antennas, if you see next to the road, those are base stations, and then there are 5, 6 antennas. So if one of them goes down, then 4 of them will be just overloaded. And this will be the case most of the time in any of the IoT device scenarios. So now you have to model depending on how you're going, how this is taking care of your device. Like if it goes down, how you're going to calculate or measure the impact of one device on other device. So, because if your final goal is to predict in next 24 hours what will happen, then you have to consider all the different scenarios, and you have to work with different algorithm models and then bring it together so that you perform really well here. So for the neighborhood dependency, we thought okay, a Markov chain also gives a very good result. So we tried different techniques on understanding the dependencies. We tried correlation matrices as well, like calculating the co-occurrences of any of those sensors or the devices. Like if device 1, when the device 1 is how device 1 is correlated to device 2. That means how it will impact on this, and if it's even working at the same time. So that means if it is working on day 1 at 10 a.m., is device 2 at the same time, first it's active, and if it's active, is it working or is it impacting it in some way? So you have to consider that. So that we calculated through correlation matrix in the initial stage, and then later on we tried Markov chain model. Then the hardware dependencies. There will be a lot of dependencies from internal failures of the device itself, not just the neighboring cells, but the internal hardwares as well. And that's why you need to consider those data sets as well. So here, just to show you. So this outage, this shows the dependency on, for each cell, how it is dependent on other cells, and how it impacted at any point of time. So this is the dependency data set. Then yeah, and this is the internal configuration data sets, like which brand, or company it is and all. But because for each company there will be different configurations. Okay. So now, once you have understood, like, okay, what method will work best for you, you have to deal with your data. And the data is just not, it never comes in the form that you want it. Yes? No, sure, please go ahead. That's right. Yes. So yes, you can do either ways. So let me show you the example here. Yes, it depends on the configuration, like I said. So what happens if you see the device, it says it's configured for a single day. That means if you have got that correlation matrix in the beginning of the day, then it's you can deal with that correlation throughout the day. So yes, yes. So just to show you like the correlation matrix. So here I created this 5 minutes of the block to see each of the alarm, because the device is mostly driven, like if any of the incident or the fault is driven by alarms or the notifications. So that's the best way to see how different devices are working together and how they're impacting each other. So if one of those alarms are impacting the other alarm, or how is it occurring at the same time, or how one alarm is triggering the other alarm, if you can understand that relationship, then you can deal with it quite well at the device level. No, it's a data exploration. So just to understand like how it's related, so that we can use some of the features in the further modeling. So each of the block here shows like how it's related and how frequently it happens, so that you can deal with the redundant data, like you get away with that, and just you focus on where it's actually impacting your device. Okay, so the data, like I said, you can go with all the sensors data, like just the dump from the sensors that you have. Then you also need to have the relationship between different sensors, that how they are interacting with each other. And then whenever the failure happens, or whenever you're getting the faults, you need to continuously log that as well, so that when you go back in the history to look into those details and improve your model or calibrate it further. Okay, so again, based on those questions, yeah. So usually we start with the normal machine learning because you don't want to give it a try. You want to try a deep learning model, keep trying until you're exhausted and you have exhausted all your resources that you have, and then you say, okay, now it's not working, and now you go back from the scratch. So start with a very simple model, even if it's deep learning, where just a normal neural network to see what's happening, how it's performing, and if you're getting good results, proceed from there. So in our case, for this network congestion, some of the challenges that I talked previously, like how they're dependent to each other, how do you put, how do you create in a form that you can utilize it in the models, will be quite important for you. Then the model. So algorithm, like what different algorithm you can try here. So because you have created a time series data here, so you can start with a traditional approach where you used to deal with the time series through ARIMA models, but it requires a lot of feature engineering for you, and it can be very exhaustive. You will be spending a lot of time and not getting much output from it. So yes, it's a good to try, but get that learning to utilize it in your deep learning model. So then, the other quickest way would be if you have done time series clustering. Have you done time series clustering, any of you? Yeah. So because most of the time, time series data will be some kind of, it has indication, like what's happening, how a set of pattern is behaving, and how it's forecasting in the future. So depending on that pattern, you can definitely, if you start utilizing the clustering method on it, then it gives also a good prediction, like what is possible and how you can explore it. But from the forecasting perspective, where you really want to forecast the next 24 hours or the next 1 month of events or the activities, in the deep learning model, it was, so I tried different approaches. I settled down on LSTM, long short-term memory, which helped me with sequence modeling to a very good accuracy. Now, so let me show you. Once you have dealt with all the data sets and you have created the combination of it so that you have transformed it into time series, and especially dealt with all those challenges of the overlapping of the time series, then it becomes really easy. You can start with the keras. You can see how it's performing in the keras, and if it's working, then you can rewrite in the TensorFlow and TensorFlow serving to put it in the production, which I will talk in a while now. So, okay, so I just generated the sequence of data in the format that I wanted to have, and then I used 2 layers of LSTM here. So I tried different configuration. I went to a level where I tried bidirectional LSTMs, and then also with the autoencoders or with some variations of it. But just found that the 2 different layers of the LSTM was working quite well, especially for this. This is very specific to your use case. Like LSTM works quite well with the sequence modeling, but you have to understand the different parameters that you need to hypertune for your purpose, and it can vary completely depending on your use case. Okay, so yeah, so looking at your losses, and then what you have to be very careful. So so I got the recall of 40%, which is really low, but in production environment where you have some severities of those incidents where it can cost a lot of money, you can actually save a lot of money with even a small amount of prediction. So that's why when you're dealing with the industrial problem cases, you have to always see what is that top 20% of problem. Because you will find that top 10% or the 20% of your problem statements or wherever your faults are, if you can deal with it, it will take away 80% of your resources, workloads, and you can really execute well on that. So that's very important that you stick to that. So if you have solved it, you can further deal with it. So here, the green ones are the actual data, the actual patterns of the time series, and the red one is the predicted one. Now, you can see it's quite off. The red ones are quite off, but it's following at least it's following the pattern. And it's off somewhere, then it's not giving that, like if I talk about the accuracy of the model, so the model had pretty good accuracy and the precision, but where you really need to take care about is the true positive rates, because you will always be able to predict what are true positives, but if you are missing out on the false negatives, then it might impact your the whole problem statement. So the best way to deal with it is also to take care of the other measures or the matrices that you want to calculate, like sensitivity, specificity. Okay, so yes? Yes. So I sampled it down. Yeah. So like at any, so say I tried both the methods, like the classification and the regression. The classification I tried for simple reason to understand if I can predict if there was because of all the data sets, if there was a congestion or not. Then the regression, I tried it for the purpose to understand if I can get closer to some of those configuration values so that I can understand that was, so I can set up a threshold. So if you have a clear binary classification, it's like either 50% or whatever threshold you set. But with the regression, you can deal with that. You can keep it closer to your value, and then you can say like, okay, this looks like a success for you, or a better result for you. So that's where I dealt with it. Okay. Cool. So this is just one use case where we dealt with the production issues. Now, when we tried, like, okay, it looks good. You have tried and tested your model. It's working fine. Now, how do you take it to the production? So especially if you have real-world scenarios, you have to deal with all those latency and the network challenges. So how you can put it in a way, or whether it's a cloud or whether it's in-premise, different architectures that you want to try. So some of these, it's very important that whenever you are working on these use cases and you want to take it to the market, you consider like where you want to deploy it. First, like where you want to deploy it. So if it's in-house or in the cloud, so you can use the best to utilize the resources, especially if you're working with the deep learning models, you have to deal with, you need GPUs, massive GPUs to train it, and then maybe for the inference, you can just use the CPUs. So how you're going to deal with between GPU and CPUs, you have to take care of that. So also how you're going to integrate your model with the different internal systems like CRM databases, because the data that will be generated be stored in some of the databases, or if it's unstructured, let it be MongoDB or Hadoop or Spark. But you have to see how you're going to integrate it. Otherwise, you will have a very interesting use case that you have successfully solved it, but it never goes to the production. It never sees the light of the day, just because, yeah, you don't have enough resources. You don't have other things in the right place. And also, when you will be continuously calibrating your model. So how you deal with the different variations of the model, how do you deal with manage different models. So that you can, like TensorFlow came up with TensorFlow serving, and that helps quite a lot to do the A/B testing and as well as how you can manage different models at the same time. Okay, so this was just one use case. Let me. So, yes? Independent in what sense? So I guess that's a kind of learning. Like I started with simple ARIMA model, and then I saw there were difficulties. Like I couldn't, if the data is growing at that scale, and if you cannot, if you're not getting the better results through your different data sets, then how do you move between different models? So with the deep learning, you reduce the amount of time you spend on feature engineering also. So that's also quite important, that if you can deal with, if you have enough time to deal with all those feature engineering. Yes? Yeah, so yes, at the at the implementation level, you deal with all the matrices that you have, but in production, you will have SMEs who will be actually working on these models. So they will come back to you and they will kick you like anything, telling like, okay, this is not working. Whatever crap you have built, it just doesn't make sense. So then you have to go back and deal with it. So, okay, so. The other use case that I have is on natural language processing, and I will quickly show you how we can put the natural language. Yes, please. TensorFlow, yes. Yes. So if you have implemented in Keras, Keras allows you to. Yes, it's because now Keras can be implemented on TensorFlow serving. So you can just export your model. You export your graph, and computation graph will be taken into TensorFlow serving. You can do that, so you can completely skip the TensorFlow modeling part. But if you further want to fine-tune those models, which is not possible in Keras, then it's not that difficult because TensorFlow has also simplified a lot actually, and you just build it in LSTM. You don't have to write LSTM in TensorFlow. There are those functions straight away. So you just to understand the clarity and the flow of the algorithm, you write it in TensorFlow. Okay. Okay, so I've got this. So while we were working on the natural language processing, also I will give you the use case that what was the problem statement for us and why. Are you guys okay for me to move on other use case? So again, okay, cool. So yes, please. We tried both of it. Initially, we didn't have enough hardwares in-house, so we deployed it in the cloud on AWS. But the costs were really massive, so we had to move back to the on-premise solution. And we just bought some servers in-house and with the GPUs, and we deployed it there. In-house, I would say, like if you configure it quite well, shouldn't be a problem because you're not training your model in the live environment. You're using inference model in the live environment. You're training offline. Okay, So the problem, yes, please go ahead.
Sorry, so you had some solution for managing multiple versions, but I didn't catch it.
Okay, so to manage so if you move your computational graph on TensorFlow serving, it's very easy to manage different models and then also different versions of it. So it's basically in a production environment, you will be working with like 10 different variations of your own one model, and then also combining those models with different models. So that's how it becomes easy in TensorFlow serving. Okay, so the problem statement here was we were getting a lot of text data, let it be social media, complaints, hello Peter, Twitter, Facebook, emails, voice calls, everything, every kind of data that you can expect of. And then we were trying to understand like how it's making sense to us. So not just chatbot, which is a rule-based, and you can further fine-tune it with your deep learning model to get better at that, but a much more improved version of it, which can understand what you're talking, how it can relate the context and make sense for you. And that's where we started exploring different approaches. So in the first place, we found that, okay, if you have a good amount of data, you can deal with it. So what we found here, so when we were computing a lot of data, especially for the financial organization, we found that a lot of time, because this is very important that you're not dealing with the machine this time. You're dealing with human, and they talk and they make different senses in a very with the same language, and you have to understand that. And then get back to them or respond to them in a way that gives them a kind of amazing experience so that they can come back to you. And if you can go even further, then what actions you can take on top of that. So if someone is just saying, okay, I've lost my card, or I have, no one has reached out to me, then there is an action related to it that, okay, he needs to be contacted. So how do you create all of it in one platform, and then how do you help your customers? So we tried, again, with a very basic approach of understanding all those conversations. So when we pulled the data, we had almost 2 million records on just email from last 2 to 3 years, and almost 5 million of data on complaints. And now it's always a lot. I don't know like what happens there. But most of the time you will see customer keeps coming back to you. And when customer keeps coming back, they get frustrated every time. They get annoyed. Like the second call, third call, and then they are like, you just cannot deal with them anymore. So that's why you have to deal with them in the first time, in the first touch point when they come to you, solve the problem, and then, yes, keep them happy so that when they come back to you for a next product and not just to complain about it. Okay, so what we found, so when we were interacting with the customers on email, on chatbot, with the agents in the call center, and what was happening? They were typing rubbish, absolutely rubbish, anything. So least you can expect. Like shorthands, least you can expect. And if I can show you some of the examples, it's crap. Now, so you can see here, spelling of certificates. If you, like, okay, good luck if you want to try all the autocorrection and spelling mistakes. Good luck. You will get all different variations of it, and the time it will consume for you in the real-time environment to deal with it is crazy. So, yes, we started with building word embedding to understand what happens. So, here what we found that a lot of time customers will never even speak the same thing. Like if they want home loan, or if they want, if they're stuck with some process, they will never say that their FICA is stuck. Their home loan is they have not got their home loan approved. They will talk about all the everything else, and then the FICA. So they say, oh, my certificates were still at the branch. I don't understand why they haven't come back to me. Then someone is talking like certification, specification, ramification, like it goes on. And it's just ratification. qualifications. So this is just one example. If you look into it, like for the cash, for the payments, and especially for the markets, it just goes on and on. So how do you relate it so that it can make sense? It can create the context for you and then give you a better idea of what's happening and how you can deal with it. So for that reason, we implement. So Google provides Glove Vector. If you're using natural language processing, you must have tried Glove Vector or the GenSim to see what's that's created on almost like 6 billion words in 100 dimensions. So, and that was the purpose we created one internally to understand like if we can create our own embedding and help our customers in a better way. So, okay, so you have created word embedding now. Now what? Like what you can use it with. So for the natural language processing, yes, you can go to an extent where you can do the classifications, the text classifications, you can do entity recognitions, you can do POS tagging either through the standard libraries like Spacey, which works quite well in production environment, or you can just you can write your even own packages for it. So yeah, so before we, so especially for the natural language processing, we didn't go to an extent to clean the data, for the reason that if we are cleaning the data, then we will lose out on all. So we were just cleaning some of the details so that we can still deal with it. So when you have a natural flow, when you have the real-time data streaming in your system, you can also deal with it. If you keep implementing very corrective methods to a very high level, then you will have to do that for the inference of your model as well. So you don't want to get into that area. So then, okay, just so what we did, once you have the word embedding, or you can create the sentence embeddings, you can create the different structures, then you start implementing different techniques on top of that, because you can consider it as now sequence, you can consider it as now images, so you can apply convolutional neural network, you can implement LSTM, you can try, again, different variations of deep learnings that can give you the good examples. Now, if you start looking at the examples here, check this. First, they mix the language, so you have to deal with that. Like, most of the time, the languages will be mixed. Now, I don't understand what is this here. Name is Maggie, Rathula is applied as student loan and last year. So most of your data will actually look like this, and you have to deal with that. You cannot say that I need a very clean data, only then I will be a data scientist and work on it. No. You get all of these, and you have to work. So then, how do you utilize? So because now you have created that word embedding that can kind of understand the relationship between different, say, paragraphs, different sentences, and that's how you create your embedding. Whether it's a word embedding, sentence embedding, document embedding, you can go to the different levels. And when you create it, you find kind of relationship. And when you start implementing deep learning model after that, then CNN comes quite handy if it's small data sets. If it's like it's one sentence, if it's sorry, I just put it wrong. If you have like long paragraphs and a lot of text, then CNN helps you to pick some of the important information from it, and utilizing embedding, it can give you a very easy classification. So that's helpful. So say you want to try summarization, text summarization, and then implement something, that will work quite good for you. But if you have very short sentences, then CNN doesn't work quite well. We tried on the same data set for both the techniques. I guess LSTM performs much way better for, say, one sentence or the two sentence where you're asking a lot of queries. Then yes. And So you do classifications. Then when you have done the classifications, if you use the GenSim library on top of your, so if you use the GenSim library, what you will find that you can also find the similar sentences, documents, text. Now, what does that mean? A lot of time, if you have, let me show you from the example. Okay, so maybe I can show the example after, if someone is keen, I can show that. So because we are running out of time, so, but yeah, when you are building these models, what you have to take care of is like, again, how you are going to take these models into the production, and it's not just how you can use the same model for different use cases, like automated email responses, very deep conversation on the chatbots, how you can interpret the models on like voice. So I've got some demos on the voice, like what we did on the voice, but I'm running out of time. But if someone is keen, I can show the demo where it works on the local South African accents as well. We trained it on 800 hours of data, and it works quite well. So, and we use different techniques. So in the deep learning. So the voice, we can show you later on. Okay, if you have a question, yeah? We are working on it, and like we can show you some results there. Okay, if there is any question, or I can, yeah, if you have any questions, maybe I can, yeah?
You mentioned spacing.
Yes.
You're using Prodigy for creating training sets.
Sorry.
Prodigy, it's exposure.
Yes, so we, like, again, it's annotating tool, and you can use it. Depending on like, because you can create one or you want to use a tool, depends. Like,
Just wondering if you've had a good experience.
we used it, but it was, again, it was a licensed tool, so we thought rather build it than pay for the license. Yes? Sorry, I missed it there. Yeah, I can share those ones. Okay, cool.
Your comment about AWS being more expensive about on-site is very counterintuitive. I'm just curious as to, was it running like a TensorFlow GPU instance that was very expensive and you decided to be cheaper locally?
Again, it depends on like how you want to utilize it. So yes, AWS gets expensive when you're not careful about it, because if you just spin some of the GPU instances, G2, G8, and then just or P2 and leave it running, then you will, like, we got like $200,000 last year, and we didn't realize where we went wrong. So we just shut it down everything, and then we said, okay, no, we will be more careful. So yes, you have to be very careful, and it can be very effective. Like if you just want to train something for a short amount of time, use very big, those large instances, train it, finish it, and then come back. So it should be fine. Yeah. Here. So we achieved, like, for the classification, so there will be like different accuracy for like different data sets. So here we achieved from the classification level for the supervised data, we had somewhere 90 to 92% accuracy, and it was working quite well. So if you can work with the word embedding pretty well and implement CNN or LSTM nicely, and if you have hyper-tuned it on enough amount of data, yes, that will actually give you very good accuracy. Yes, see, the business case here was like we started with simple complaints. Then whatever queries we were getting on the call center. So all those queries we started understanding and analyzing it and just trying to make sense in the real time. Then we went even further to implement it in the chatbot, in the voice bots, and those kind of stuffs. Yeah.
I was going to ask if you've considered using fast text.
Sorry.
Fast text.
Yes. So fast text help. That's a very good question. And if you work on a lot of word embeddings or those text data, then fast text helps you on creating those very quickly. The challenges with the fast text that we found was it's mostly CPU driven. Like the one that you get from Facebook, it's with the CPU. So at one point, we really got a lot of cost from AWS was we were running 64 cores on AWS just to train the word embedding on fast text. So yes, so fast text is good. Like you can create your vectors very quickly through the fast text and then expose it to the GenSim, or you can expose it to any other library. It's very easy after that. Instead of you creating everything on your own, or if you're trying TensorFlow to create your embedding, it takes a very long time. It can take like 2-3. So we tried it with TensorFlow. It takes 2-3 days to create that whole embedding. We had approximately 5 million tokens. So yeah, so 5 million sentences, sorry. And then with 80 million tokens or something. So that took 3 days for us, but when we tried fast text, it was actually an hour with 64 cores because it's not GPU, it's CPU driven. Okay, thank you. Thanks all. Oh, sorry, just the last question.
If there is time, could you explain, you were talking about the Markov chains and the different ensembles we're using for the first example.
Okay.
Could you maybe just tell us what that ensemble entailed?
Okay, so for the first use case for the network congestion model, where we tried to understand like how different devices are impacting each other. So we started with like co-occurrences metrics, simple like how do you create that if the both devices are active at the same time and if they are creating problems for each other. Then we went to correlation metrics, and we again tried different techniques to find that correlation. Then at the later stage, we found that the Markov chain was also helpful in understanding that relationship between those devices, like how one device is impacting the other device. So, but we couldn't put a Markov chain in like production. We had to settle down on correlation. But I can give you more details separately. Yeah. Okay. Yes. So when we initially created co-occurrences metrics, then we tried to create the best metrics possible, and with the 5 minutes interval, it looked ideal for us. But the problem was we were not able to create it at that speed because it was very computationally expensive process, and we had. We tried different techniques, it didn't work. So what we settled down on is creating those sparse vectors. So sparse vectors was easy to create for the correlation. So like you do one hot encoding for the text, the similar way you start creating a sparse of the dependencies. Okay. Cool. Thank you. Thank you.